Hello everyone, this is Harsha from Sri Venkateswara College of Engineering. Today I am here to present you a video assignment on a swap instruction, and we will discuss about swap instructions and other instruction of ARM instruction set, and we also will learn the example of 3.22 in the swap instruction in our book. So the introduction to ARM instruction set. The instruction set of our architecture is a fundamental for building fast, efficient computers that optimize memory and processing resources. It specifies the following supported capabilities like instruction, data types, processors, registers, main memory, hardware, input and output model, addressing modes, etc. So the programs and system engineers rely on the ISA for guidance on how to program various activities. Instruction sets work with other computer parts of a computer, such as compilers and interpreters. Those components translates high-level programming code into machine code that processor can understand. We think of the ISA as a programmer's gateway into the inner working of a computer. So the ARM instruction sets consist of many ARM instructions, data types, processor registers, main memory, hardwares, inputs and output models, addressing modes, etc. So let us discuss what is load store instructions. The load store instruction transfer data between memory and the processor registers. These are three types of load store instruction: single register transfer and register transfer, multiple register transfer, and swap. So the single register transfer, the single registers transfer, these instructions are used for moving a single data item in and out of a registers. The data types supported are signed and unsigned words, which is exactly 32-bit, half word 16-bit, and bytes. Here are the various load, store, single register transfer instructions. The syntax is B is branch and RD is read, and addressing 1. LDR is load register, SB, H, SH, and RD address in. As you can see the diagram, this is the diagram for input and output getting in the registers. So this is learned before in the digital design and computer organization. So the multiple register transfer. Load store multiple instructions can transfer multiple registers between memory and the processor in a single instruction. The transfer occurs from a base address registers Rn pointing into memory. Multiple register transfer instructions are more efficient from a single register transfer for moving blocks of a data around the memory and saving and restoring context and stacks. So as you can see the multiple registers here, which is used for transferring the data. We can here see the 4x1 multiplexers and 4x1 multiplexers. We have four 4x1 multiplexers. So the 4-line common bus are used. The bus systems for 4 registers are given in the figure. So this is register D, this is register C, this is register B, and this is register A. The A, B, C registers are connected to the multiplexers, 4x1 multiplexers, and form multiplexers of 4 multiplexers, which basically performs multiple registers transfer. So next we have swap instruction. The swap instruction is a special case of load store instruction. It swaps the contents of a memory with the contents of a registers. So as you know, in the field of computer science, the swap, or on the field of the programming, the swap instruction or the swap function is used to swap two numbers. When we can swap A and B by placing the value of B into A and placing the value of A into B. So this process is called as swapping. So the swapping instruction is also performed in this in the ARM instruction set. So this instruction is an atomic operations. It reads and writes a location in the same bus operations, preventing any other instructions from reading or writing to that location until it completes. The syntaxes of the swap instructions are SWP, which is called a swap program or swap operations, or swap the memory and the registers. So we use in the brackets, in the flower brackets, we use the branch and empty bracket to swap anything. So then RD is used to read, and RM is the memory, and RN is the registers used. So the swap a word between memory and a register. This SWP keyword is used to swap a word between the memory and the registers. So TMP is nothing but the temp, and MEM32 is nothing but the memory 32, which is stored in the RN. Memory 32 RN is equals to, or assigned, RM is assigned to RN. So the temp is moved to the RD. So next we have SWP, the B. The swap B is nothing but, it's the swap operations is held with the byte operations. The swap a byte between memory and a register. So TMP, which is nothing but temp or a temporary registers. Then memory 8 RN, this is the registers used to swap the two registers. The RN and RM and RDs are swapped regularly. So swap cannot be interrupted by any other instructions or any other bus access. So it holds the bus until the transaction is completed. So this is the swap instructions performed. As you know, I had an example to explain, which is example 3.22. So the swap instruction loads a word from a memory into the registers R0 and overrides the memory with the registers R1. So as you can see, the swap instruction loads a word from the memory into the registers R0 and overrides the memory with the registers R1. So we have a pre-statement or the pre-code which is written here. So we have memory locations of the values 0x9000. This is hexadecimal value, which is stored with the 0x12345678, which is a random hexadecimal value. So R0 is equals to 0 and R1 is equals to 0x1111222. And R2 is 0x000900. So the swap function is called, which performs R0, R1 is equals to R2. This brackets here is used to get the value from the R2 location. So the R2 value is swapped with the R1 value. Then R2 value swapped with R1 and R1 is swapped with R2, which is overall stored in R0 or R0. Then post operations are again after swapping the numbers. So we have in the memory 32 0x9000, we have at this memory locations, memory that is 32-bit memory location, we have 0x1111 and 2222. So as you can see here, R0, R1, R2 are the values, and R1 and R2s are swapped and stored in the R0 or the R0. This instruction is particularly useful when implementing the semaphores and mutual exclusions in an operating systems. As you learned in the OS, which is operating systems, you can see from the syntax that these instructions can also have a byte size qualifier B. So this instruction allows for both a word and a byte swap. As you can use for the byte operations, you can use SWPB, which perform the byte operations to swap. So this swap is done by SWP keyword, and the R1 and R2 is swapped, and the value is stored in R0. So the swap value is stored in R0. Okay, thank you. This was my topic for today, and any doubts do comment in the comment section. Have a nice day. Thank you.